Okay, so 4.1 is all about maybe something you may or may not have been exposed to, but the idea of something called a matrix. All right, the plural is matrices, as you can see, but this is one, two matrices. This is one matrix. This is another matrix, okay? So that really all a matrix is a set of numbers arranged a certain way, all right? So it's a set of numbers inside, when you write them, it's a set of numbers inside two brackets, a set of numbers inside two brackets. And the order that they're put in there is relevant. So if I was to switch this 4 and the 2/3, that would be a different matrix. Okay, so where they are in the matrix matters. Okay, and how big each row and column is. So yeah, first idea in here is what's a row and what's a column. So this matrix has two rows. So this is a row, this is a row. Oops. Okay. And then it has three columns. 1, 2, 3 columns. Okay. 1, 2, 3. All right, so that's how you refer to different parts of a matrix. It has rows and it has columns. Okay, matrices are always rectangular or maybe square. In fact, these are both called square matrices down here on the bottom of the screen. As hopefully is apparent why that would be the case. Okay, so I have two square matrices down here. This is how we refer to these, is we say rows then columns. So this is a 2 by 3 matrix. This is a 3 by 2 matrix. So this is a 3 by 2 matrix here, and that's the dimension. So when we say the dimensions of a matrix, it's something like we say 3 by 2. Okay, 3 by 2. This would be a 2 by 3. Okay, this down here would be a 2 by 2. And this would be a 3 by 3. So as you might guess, a square matrix has the same number of rows and columns. So it's always 3 by 3, 4 by 4, 5 by 5, whatever. That's how you know it's a square matrix. It's got the same number of rows and columns. All right. So there's some introductory terminology. Like I said, it really can be any number. So that's why I got a little creative with the pi, cube root of 7, 1,000, 0. Any number can be in the matrix. And then we have rows go left and right, columns go up and down. Okay, and in Common English, sometimes we kind of interchange these two things, rows and columns. But that's wrong in math. Sometimes math, usually in math we have to be more precise. And here's a good example of that. You can't just interchange rows and columns. Columns go up and down in a matrix. Rows go left and right. Okay. Each little number in the matrix is called an element. So there's 9 elements in here. Most of them are zeros and the rest are ones, of course. But for instance, in matrix B, there are 9 elements. In matrix A, there are 4 elements. All right, 6 and 6 up here. By the way, it's pretty common, and it's not just matrices where this works, or where this happens, is that it's really common to use a capital letter to refer to the matrix as a whole. Whenever something is fairly complicated and has a lot going on, and you don't want to necessarily rewrite the whole thing over and over and over again, even if you want to refer to it over and over and over again, then you use a capital letter a lot of times to represent something like that. It's exactly what we have going on here with matrices. A lot of times, capital letters represent matrices. Okay, so matrix A and matrix B. And so we want to refer to not the whole matrix, but just a part of it. In other words, it's one of the elements, one of the 9 elements, or one of the 4 elements. Then we use the corresponding lowercase letter. So lowercase a, in the context of matrices, is referring to one of the elements in this matrix, and in this case it's 5. And so we always say which row it is and then which column it is. So it's second row, first column. So the order that you write these things matter, just like, for instance, an ordered pair. In fact, it's a lot like that. Row, then column. So it's second row, first column, right here. So that's why it's 5. If I switch it up, it's a different number. Okay. So if it's 1, 2, first row, second column, that's 4. So that's how you refer to specific elements in a matrix. Okay. Elements are different things that are in, are the numbers that are in the matrix. Last but not least, there's 3 like special types here, and I mean it's not super special, but this is called a column matrix because it consists of 1 column. Okay, this is a row matrix. Okay, and so you could, this could be 30 things long, and it wouldn't matter. It'd be a row matrix, a 1 by 30 row matrix. In this case, it's 1 by 5, of course. This is a 3 by 1. This is a 2 by 3 zero matrix. So it's literally everything is in the matrix is 0. Then we call this a zero matrix. So this is a column matrix, a row matrix, and a zero matrix. And the dimensions here could be different. This could be a 500 by 1 column matrix. This could be a 1 by 500 row matrix. And really the dimensions of a zero matrix could be anything, as long as everything in there is a 0. And actually, I forgot to talk about it. This is an example, and you don't need to know that quite yet. This right here is an example of an identity matrix. If I could write, that'd be great. Identity. Okay? So specifically, the identity matrix is one where this diagonal, starting at the top left, ending at the bottom right, it's all ones, and then everything else is 0. So to be an identity matrix, one thing is you got to be a square matrix first off, and then specifically, very specifically, this diagonal from top left to lower right has to be all ones, and then everything else has to be zeros. And then that'll be important later, but I thought I'd introduce that today, even though I don't think there's any reference in it to it in this first section for 1. All right, equality. What's it mean for 2 matrices to be equal? Well, it's a very strong statement for 2 dimensions matrices to be equal, because all the parts have to be same. So the corresponding element, first off, they have to be the same dimensions. So a 2 by 2 and a 2 by 2 are equal, or can be equal. Okay, but not only that, but each corresponding thing has to be the same. So, okay, so the 1 equals the 1 there. Okay, and then 5 equals 5. 4 equals 4, -3 equals -3. So the corresponding guys have to be equal. The corresponding elements have to be the same. If one thing is off, then it's not. So why does this not work? They're both 2 by 2 matrices. They're the same dimensions. Okay? And they have all the same numbers, but they're not in the right spot. Okay? 1 and up 1 and 4. So the first row, first column element, they're different. First row, second, I made it too big, it doesn't match up. First row, second column, they're different. Second row, first column, different, and so on, all right? So, not only do you have to have all the same numbers, not only do you have to have the exact same dimensions, but each corresponding element has to be the same. So this is equal. Hopefully that's kind of self-evident, it's the exact same thing twice. This looks close, but not quite. All right, it has all the same numbers, the dimensions are the same, but the numbers aren't in the right spots. All right, so notice all I did was switch to columns, basically. So changing anything makes it not equal. So the only substantive thing you really have to do in this section is solve equations, or systems of equations, maybe, that are defined by matrices. And so this is a matrix equation. If you have 2 matrices equal to each other, we call that a matrix equation. And so here you go. And what this implies is 2 different things, really. Okay, this is well, let me actually, a little bit of a review from earlier in the video. This is a 2 by 1, right? So this is a 2 by 1. And so is this 2 by 1. So that's okay. And so, well, they don't look the same, but this little equal sign is implying that they are. So what this implies is it implies 2 things. One for the top, that x plus y has to equal 10, and that x has to equal 2y minus 8. All right, and so a good chance that your do now tomorrow will be to solve this system of equations to answer the question. All right, if you have trouble with that, then that's bad news because that's literally what we're just testing on. Solve this by, and really the way to go would be substitution. So your do now is likely to be exactly this right here. Solve this matrix equation by substitution. All right, so there you go. That's 4-1.